Right now, on the other side of the Pacific Ocean, the seafloor off the coast of Russia is shaking in a pattern that almost exactly mirrors what California started doing 24 hours ago. 8 earthquakes above magnitude 4.5 in roughly 36 hours, all inside a 50-kilometer box, all on a segment the Japan Meteorological Agency has been officially watching since last year's magnitude 8.8 event left it loaded. The most recent earthquake came in just hours ago. The cluster is not slowing down, and on the other corner of the same plate that covers 20% of the surface of this planet, the southern Cascadia margin is also still adding events on the same 48-hour clock. 2 simultaneous clusters on the 2 opposite locked corners of the largest plate on Earth, both still developing, both on segments already officially flagged. What that means, and what every seismologist watching this pattern tonight is quietly trying to figure out, is exactly what this video is about. One thing before we get into it: if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs, and let me know in the comments where you're watching from. Now, let's get into it. Part 1. Tonight. At 17:13 Universal Time. At 17 hours and 13 minutes, Universal Time on June 4th, 2026, a magnitude 5.1 earthquake struck the seafloor off the eastern coast of the Kamchatka Peninsula in the Russian Far East. The epicenter, at 51.88 degrees north latitude and 159.18 degrees east longitude, sat 10 kilometers below the seabed in the box of ocean, where the Pacific Plate plunges beneath the Okhotsk microplate at one of the fastest subduction rates on Earth. The report came in from the GFZ German Research Center for Geosciences, the Central German Seismic Authority, and it arrived more than 36 hours after the same patch of ocean had already started to wake up. By the time that magnitude 5.1 was logged, at least 7 other earthquakes above magnitude 4.5 had already been recorded inside the same 50-kilometer box. The cluster was not slowing down. It was still adding events. That is the first thing to sit with tonight. The cluster off the Kamchatka coast is still adding events. The magnitude 5.1 at 17:13 Universal Time is not the end of something. It is the most recent visible marker in something that is still developing while this recording is being made. And on the other side of the world, on the other corner of the same plate, the seafloor off Northern California is also still adding events. Another magnitude 4.5, another magnitude 4.6, off the coast of Petrolia, California, in the same patch of ocean where a magnitude 5.7 and a magnitude 5.1 had struck the morning of June 3rd. The independent observers who watch the United States Geological Survey feed in real time have been logging the additional events through the evening of June 3rd Pacific Time and into the morning of June 4th, and the tally on the California side is now sitting at roughly 7 earthquakes inside a tight cluster off the southernmost corner of the Cascadia subduction zone. 2 clusters, 2 sides of the same plate, both still active, both still adding events. The window between the first arrivals on the California side and the most recent arrival on the Kamchatka side is less than 48 hours. The distance across the open Pacific Ocean between the 2 clusters is approximately 7,500 kilometers, and between them, holding them apart and holding them together, sits the largest single mechanical object on the surface of this planet, the Pacific Plate. This is the story you're about to hear. Yesterday's nightly debrief covered the California cluster. What happened, where it sits in the 326 years of Cascadia quiescence, what the elevated tremor counts mean for the southern locked zone. Tonight is different. Tonight is what is happening on the other corner of the same plate, while the world is still focused on California. Tonight is the cluster that almost no one in the West is reporting yet, the one developing in real time off the coast of Russia, on the same 48-hour clock as the California events, on a segment that is already under an active megaquake advisory from the Japan Meteorological Agency. Tonight is the question that no seismologist watching this pattern has yet answered out loud. Whether 2 clusters firing on opposite corners of the same plate in the same 48-hour window mean something, or whether they are the most ordinary thing in the world, the catalogue accidentally lining up because the catalogue occasionally lines up. The honest answer to that question is that the literature cannot resolve it. The honest answer is that the simultaneity is statistically unusual but not unprecedented, that each cluster has its own local mechanism that explains why it is happening on its own segment, and that the question of whether the simultaneous visibility means more than each cluster considered alone is the kind of question that the formal stress transfer literature treats with a great deal of caution. We're going to walk through what the literature says. We're going to walk through what the energy arithmetic forecloses. We're going to walk through the three readings of this pattern that the seismological community would consider defensible, and we're going to land at the end on what every person watching the catalogue tonight is actually asking themselves, whether they are saying it out loud or not. Before we get there, though, there is a thing to understand about the moment we're sitting inside. The Pacific Plate moves at approximately 7 to 10 centimeters per year in a roughly west-northwest direction across the surface of the Earth. It has been moving that way for tens of millions of years. The energy that drives that motion is dispersed across approximately 103 million square kilometers of plate area, equivalent to roughly 20% of the planet's surface. The plate's two long subducting margins on the west and northwest, the trenches that run from New Zealand through Tonga and the Marianas up through Japan and the Kurils into Kamchatka, are where most of that energy is converted into earthquakes. The plate's eastern margin, where it transitions from the East Pacific Rise as a spreading centre to the small fragmenting Gorda Plate at the southern Cascadia corner, is where the rest of the energy comes out. The two opposite corners of this plate are not, in a deep mechanical sense, fully independent. They are connected by the rigid body between them. They are part of the same machine. What you're going to see tonight is what happens when both ends of that machine produce visible catalogue activity in the same 48 hours. Whether that visibility is meaningful, or whether it is a kind of optical illusion produced by two independent clocks happening to fire at the same time, is the question that the rest of this video investigates. The first thing to do, before we can ask anything bigger, is understand exactly what is happening in the box of ocean off the Kamchatka coast right now. Because that, more than anything else tonight, is what the global catalogue has not yet caught up to. Part 2. The box that just got 8 earthquakes in 36 hours. The cluster sits in a small patch of the Pacific Ocean, centred roughly on 51.5 degrees north latitude and 159.5 degrees east longitude. To make that location concrete, hold a globe in your mind. Find Japan. Move your finger north along the chain of Russian islands that arcs from the northern tip of Honshu up toward the long thin peninsula that hangs south from the eastern Siberian coast. That peninsula is Kamchatka. The cluster sits in the ocean directly off the southeastern coast of the peninsula, about 150 to 200 kilometers south-southeast of the city of Vilyuchinsk, which sits on Avacha Bay near the southern tip of the peninsula. Vilyuchinsk is the home base of the Russian Pacific Fleet's submarine forces. Petropavlovsk-Kamchatsky, the regional capital, sits a few kilometers north of Vilyuchinsk on the same bay. Together, those two cities hold the bulk of the peninsula's 300,000 or so residents. The cluster spans approximately 50 kilometers from north to south and a tighter distance from east to west. Inside that small box, here is what the international seismic catalogues have logged across the last roughly 36 hours. We will go from the most recent event backwards through the cluster. The most recent event at 17 hours and 13 minutes Universal Time on June 4th was the magnitude 5.1 reported by the GFZ German Research Center for Geosciences. Epicenter, 51.88 degrees north latitude, 159.18 degrees east longitude, depth 10 kilometers. That depth places the event right at the shallowest end of the megathrust interface zone, the depth band where the locked patch between the Pacific Plate and the Okhotsk microplate sits. A 10-kilometer depth event in this geometry is the canonical interface earthquake signature. It is not a quirky deep slab event. It is not a peculiar near-surface oceanic crust event. It is a textbook megathrust interface event at the shallow end of the interface depth range. Working backwards from there, earlier on June 4th at 02 hours and 32 minutes Universal Time, the Russian Academy of Sciences Geophysical Service, abbreviated GISRAS, logged a magnitude 4.6 at 51.42 degrees north and 159.64 degrees east at 20 kilometers depth. 2 hours later, at 04 hours and 34 minutes Universal Time, the same agency logged a magnitude 4.5 at 51.72 degrees north and 159.62 degrees east, depth 45 kilometers. That second event is interesting because the depth is much deeper. 45 kilometers is well into the upper portion of the subducting Pacific slab itself, not the interface above it. Step backwards through the night before, on June 3rd, and you find the largest event in the cluster so far. At 17 hours and 23 minutes, Universal Time on June 3rd, the European Mediterranean Seismological Center logged a magnitude 5.2 at 51.634 degrees north and 159.403 degrees east, depth 20 kilometers. The same event is catalogued by the United States Geological Survey under event identifier US 7000 SQ-CW, with the same magnitude 5.2, listed as 188 kilometers south-southeast of Vilyuchinsk, depth recorded at 10 kilometers on the USGS side. The small variation in depth between the two authorities, 20 kilometers from EMSC, 10 kilometers from USGS, reflects normal cross-cataloguing variability. Both agencies are reporting the same physical event from different stations and different inversion processes. The variation is well within the typical error envelope. The point is that the magnitude 5.2 is the largest event of the cluster so far, and it occurred on the night of June 3rd Universal Time, which corresponded to early morning of June 4th on the Kamchatka coast. Roughly 45 minutes later, at 18 hours and 9 minutes Universal Time on June 3rd, the European Mediterranean Seismological Center logged another event, a magnitude 4.7 at 51.574 degrees north and 159.5075 degrees east, depth 20 kilometers. The USGS catalogues a corresponding event as 181 kilometers southeast of Vilyuchinsk at 25.672 kilometers depth, under event identifier US 7000 SQDB. The Russian Academy of Sciences also logged a magnitude 4.6 at 17 hours and 32 minutes Universal Time on June 3rd at 51.2 degrees north and 159.84 degrees east, depth 40 kilometers, and another magnitude 4.6 at 20 hours and 15 minutes Universal Time at 51.49 degrees north and 159.99 degrees east, depth 40 kilometers. The European Mediterranean Seismological Center adds a magnitude 4.5 at 20 hours and 3 minutes Universal Time on June 3rd at 51.5318 degrees north and 159.6651 degrees east, depth 32 kilometers, and the USGS catalogues an additional magnitude 4.5 event under identifier US 7000 SQEC, listed as 179 kilometers south-southeast of Vilyuchinsk, depth 35 kilometers. If you add those up, and accounting for the small differences between catalogues that are just different agencies reporting the same underlying events from different stations, you get a cluster of approximately 8 to 9 confirmed magnitude 4.5 and above earthquakes in roughly 36 hours, inside a box less than 50 kilometers across. That is not the activity rate of a normally behaving piece of seafloor. That is the activity rate of a fault system that is doing something. Now, the depth distribution of those events tells a story by itself. The shallowest event, the most recent magnitude 5.1, sits at 10 kilometers. Several of the mid-cluster events sit at 20 to 25 kilometers. Some sit at 32 kilometers. Some sit at 35 kilometers. The deepest event in the catalogue sits at 45 kilometers. That range, 10 kilometers to 45 kilometers, spans almost the entire vertical extent of the megathrust interface and the upper portion of the subducting Pacific slab at this longitude. The interface itself, where the Pacific plate locks against the Okhotsk microplate, sits in that depth range. Above 10 kilometers is mostly oceanic sediment and uppermost crust. Below 45 kilometers is mostly slab mantle. The cluster has activated essentially the entire portion of the interface that is mechanically capable of brittle failure on this segment, and that activation pattern matters. A single rupture, like a small earthquake at one fault patch, followed by a sequence of aftershocks decaying around it, would typically produce events within a much narrower depth range. The same patch fires multiple times as stress redistributes locally. What we are seeing on the Kamchatka side is different. We are seeing events at 10 kilometers, at 20 kilometers, at 32 kilometers, at 45 kilometers, all within the same 50-kilometer horizontal footprint, all within 36 hours. That depth spread is more consistent with a broader regional stress increment activating multiple discrete fault patches across the full interface than with a single patch firing and then decaying. Whether that broader regional increment is the natural ongoing settling of stress redistribution from something that happened a long time ago, or something else, is the kind of question that the formal stress transfer literature debates in papers that take 6 months to a year to write. For tonight, the observation alone is enough to flag. The temporal stacking is also worth pausing on. The cluster did not produce all its events in the first 6 hours and then taper. The cluster produced events on the evening of June 3rd Universal Time, the night of June 3rd into June 4th Universal Time, and again on the afternoon of June 4th Universal Time, in 3 or 4 distinct visible pulses across the 36-hour window. Each pulse is separated from the next by enough time that they are not the immediate aftershocks of a single main shock under Omori's law, which predicts an aftershock rate that decays roughly as the inverse of the time since the largest event. The Omori prediction for this cluster, if it were a single main shock plus aftershock sequence, would have aftershock rate dropping steadily across the 36 hours. That is not what is happening. The cluster is sustaining its event rate, not tapering it. These 3 observations, the dense small box footprint, the full depth interface activation, the sustained temporal rate, are the technical signatures of a fault system under sustained or recently elevated stress, not a fault system that fired once and is decaying. Whether the source of that stress is local to this segment alone, or whether it is part of something larger that connects to what is happening on the other side of the Pacific Ocean tonight, is the question we are working toward. To get there, we need to understand, first, where this segment sits, geographically, tectonically, historically, and why a cluster of moderate earthquakes off the southeastern coast of a Russian peninsula matters for a viewer sitting in California or Ohio or Texas or anywhere else in the United States tonight. Part 3. Where Kamchatka sits on the map and why that matters. For most viewers, Kamchatka is one of those places on a map that exists in a kind of geographic blur. It is far away. It is Russian. It is in the part of the world where Russia meets Alaska across the Bering Sea. It is the place where some of the largest brown bears on the planet live, where there are more active volcanoes per square kilometer than almost anywhere else on Earth, where the cities on the southern coast face out across an ocean that takes a very long time to get to anywhere familiar from. That blur is fine for most purposes. It is not fine tonight, because the precise position of Kamchatka on the geological map of the world is exactly the thing that makes this cluster worth paying attention to. The Kamchatka Peninsula juts south from the eastern Siberian coast into the Pacific Ocean. It is roughly the size of California in geographic area, about 470,000 square kilometers, but it holds only about 300,000 people, most of them concentrated in the south near Petropavlovsk-Kamchatsky and Vilyuchinsk. The northern 2/3 of the peninsula is essentially uninhabited tundra and volcanic mountain country, much of it inside the Kronotsky State Biosphere Reserve. The southern third holds the population centers, the Russian Pacific Fleet bases, the regional airports, the ports that connect the peninsula to the rest of Russia and to the international fishing economy of the North Pacific. Now look at where the peninsula sits in the larger geological architecture of the Pacific Rim. The peninsula sits directly above the Kuril Kamchatka Trench, which is the subduction zone where the Pacific Plate dives beneath the Okhotsk microplate. The trench itself runs offshore, parallel to the coast of the peninsula, at a distance of roughly 150 to 200 kilometers from the shore. The trench is approximately 10,000 kilometers in total length, running from the northern tip of Hokkaido in northern Japan up through the Kuril Islands chain, along the eastern margin of Kamchatka, and around the Komandorsky Islands toward the Aleutian Trench. It is one of the longest and one of the most active subduction zones on the planet. The mechanical situation underneath the peninsula is this. The Pacific Plate, the largest plate on Earth, is moving in a roughly west-northwest direction at approximately 7 to 9 centimeters per year, as measured at the Kuril-Kamchatka margin. That convergence rate is among the fastest of any subduction zone in the world. By comparison, the Cascadia margin in the Pacific Northwest of the United States, the same kind of subduction zone but on the other corner of the same Pacific Plate, is converging at about 2.5 to 3 centimeters per year. The Kuril-Kamchatka rate is roughly 3 times faster. That means the Kuril-Kamchatka Trench accumulates the same amount of elastic strain in about 1/3 of the time it takes Cascadia to accumulate the equivalent strain. It also means the Kuril-Kamchatka Trench produces large earthquakes more frequently than Cascadia, a great deal more frequently. The fast convergence rate has practical consequences. The Pacific Plate is being shoved beneath Kamchatka so quickly that the locked patches on the interface, The patches where the two plates are stuck together accumulating elastic strain because friction is preventing them from slipping, fill up with strain on relatively short timescales. The recurrence intervals for magnitude 8 and above earthquakes on individual segments of the Kuril Kamchatka system are typically in the range of 70 to 150 years for each named segment. For comparison, Cascadia full margin recurrence intervals are typically in the range of 200 to 600 years. The Kuril Kamchatka system, in other words, is on a faster failure clock than Cascadia is. It produces large events more often. It has been producing large events for as long as the historical record exists, and well before that into the paleoseismic record. What this means for tonight is that the Kuril Kamchatka system is a place where the appearance of a moderate earthquake cluster is not a minor catalogue observation. It is a place where the geological clock runs fast enough that elevated activity near a known loaded segment has earned attention from the National Seismic Authority. We're going to get into that, the actual official advisory in effect, what it covers, when it was issued, why it has not been lifted, in a few minutes. But first there is a piece of context that connects this trench to the other side of the Pacific in a way that most viewers have never really thought about. The Pacific Plate is a single solid object. That sentence sounds simple, but the implications of it are not. The plate is approximately 103 million square kilometers in area, equivalent to about 20% of the entire surface of the planet. It is by far the largest tectonic plate on Earth. It is, mechanically, a single rigid body, the same way the North American plate is a single rigid body that extends from the western coast of the United States all the way across the Atlantic Ocean to the western coast of Iceland. The Pacific Plate is not an assemblage of independent tectonic blocks that happen to be next to each other. It is one continuous solid sheet of oceanic lithosphere that has been moving as a coherent unit for tens of millions of years. The plate is driven primarily by two forces. The first is slab pull. At every subducting margin, Japan, the Kurils, Kamchatka, the Aleutians, Tonga, Mariana, the leading edge of the plate is being dragged down into the mantle by the negative buoyancy of the cold, dense slab as it descends. That downward pull is transmitted up through the slab and into the plate as a sustained mechanical force that pulls the plate westward and northwestward across the surface of the Earth. The second is ridge push. At the East Pacific Rise, which is the spreading centre on the plate's eastern margin, hot mantle rises and new oceanic crust is formed, and the geometry of that elevated ridge creates a sliding force that pushes the plate westward. Slab pull and ridge push together account for essentially all of the energy that drives Pacific Plate motion. What that means physically is something the literature is very careful about saying out loud because the implications can be misread. The two opposite margins of the Pacific Plate are not independent. They are mechanically connected through the rigid body of the plate between them. A change in the slab pull on the western margin, say a large earthquake at the Kuril Kamchatka Trench that abruptly redistributes some stress along the subducting slab, propagates through the plate as elastic stress at a speed limited by the speed of sound in rock, which is about 5 to 7 kilometers per second. A change in ridge push on the eastern margin, say a redistribution of stress at the Mendocino Triple Junction, where the East Pacific Rise meets the southern Cascadia subduction zone, propagates the same way. The plate is a single piece. What happens at one end is, in principle, communicated to the other end. Now, the speed of sound in rock is fast enough that the propagation itself is essentially instantaneous on the scale of weeks. The question, though, is not whether information can travel across the plate. The question is whether the stress changes involved are large enough to produce detectable effects at the opposite margin. And on that question, the literature is much more cautious. We will get to the actual numbers in a few minutes. What the remote dynamic triggering literature says about how far stress effects travel from large earthquakes, what magnitudes of source event produce detectable triggering at hemispheric distances, why both of the present clusters are below that magnitude threshold. The point for now is just this. The Pacific Plate is a single object. Its two opposite locked corners are connected through it. The question of whether what is happening on one corner has anything to do with what is happening on the other corner is, at the level of basic mechanical possibility, a legitimate question to ask. It is not a fringe question. The literature treats it carefully. That brings us back to the cluster off the Kamchatka coast tonight. The cluster sits on the southern portion of the Kuril Kamchatka Trench, on what is functionally the southern terminus of the Kamchatka segment proper, in or immediately adjacent to a segment that has been under active institutional megaquake advisory from the Japan Meteorological Agency since the events of last year. The cluster is sitting on a piece of fault that is already being officially watched, and the cluster is doing exactly the kind of thing that the entities watching it would watch for. Moderate magnitude events activating the full interface depth range, sustained event rate, tight spatial footprint, no Omori decay. The cluster is, on its own, a notable thing. The cluster is also happening at the same time as another cluster on the other corner of the same plate, and that is the part that, if we stop being too careful and just ask the question the audience-facing instinct is already asking, deserves an honest investigation. Before we get there, though, we have to talk about the other corner, because what is happening on the southern terminus of Cascadia, on the California-Oregon border in the open ocean off the Mendocino Triple Junction, is the foundation that makes the Kamchatka cluster mean what it means. Part 4. The other side of the mirror. Yesterday's nightly debrief covered the California cluster as its primary story. If you're watching tonight as a returning viewer, you have the context loaded. You know what the Mendocino Triple Junction is, the place where the Pacific Plate, the Gorda Plate, and the North American Plate meet at a single geological point off the coast of Northern California. You know what the Gorda Plate is, the small, internally deforming three-sided piece of oceanic lithosphere that sits at the southern terminus of the Cascadia subduction zone, being squeezed between the Pacific Plate to the west and the much larger North American continent to the east. You know what the southern Cascadia margin is, the locked portion of subduction zone interface that runs from the Mendocino Triple Junction north along the coast of southern Oregon, where the Cascadia subduction zone proper begins. You know that it has been 326 years and 4 months since the last full margin rupture of the Cascadia subduction zone, in January of 1700, an event we have documented from Japanese coastal records of the orphan tsunami that crossed the Pacific from a North American source. You know all of that, so we are not going to reteach it tonight. What we are going to do is name what is still active on the California side as of the most recent observation cycle, set it next to what is active on the Kamchatka side at the same moment, and let the geometric symmetry do the work. Because the symmetry is what the title of this video is about. The symmetry is the observation that everything else in this video is trying to make sense of. The California cluster has produced approximately 7 earthquakes above magnitude 4 in the past day and a half. The largest was the magnitude 5.7 off Pistol River, Oregon, on the morning of June 3rd Universal Time. The second largest was the magnitude 5.1 off Petrolia, California, in the same offshore corner a few hours later. And as of the late evening of June 3rd Pacific Time, the independent monitoring of the United States Geological Survey feed has logged additional events of magnitude 4.5 and 4.6 in the same offshore Petrolia and Gorda Ridges system. The cluster did not stop. The cluster kept adding events through the evening of June 3rd and into the morning of June 4th. The most recent magnitude 4 and above event on the California side is, at the time of this recording, only a few hours older than the most recent magnitude 4 and above event on the Kamchatka side. The two clusters are running on the same 48-hour clock. They are running on opposite sides of the same plate. They are both still active. Now here is the piece of the California side that connects most directly to what we just covered about Kamchatka. On the California margin, the past month has shown elevated episodic tremor and slow slip on the deeper interface beneath the locked southern Cascadia segment. The Pacific Northwest Seismic Network and the United States Geological Survey track these events through the Pacific Northwest Seismic Network Tremor Catalog. Episodic tremor and slip is not an earthquake in the brittle failure sense. It is a slow, sustained vibrational signal that comes from creep on the deeper portion of the interface, the portion below the locked patch, where the two plates are slowly slipping past one another over weeks to months rather than rupturing instantly. The geophysically relevant fact about tremor and slow slip is that every cycle of slow slip on the deeper interface transfers a small but measurable increment of additional Coulomb stress upward onto the shallow locked patch above it. Tremor counts on the deeper interface are in effect a slow load applied to the upper locked zone. The independent observation cycle has logged approximately 2,694 catalogued tremor events in the past 30 days on the Cascadia interface, with the spatial centroid of those events concentrated beneath the locked southern segment that runs from Northern California through the southern coast of Oregon. That is a heavy tremor month, and the moments when the southern Cascadia margin has produced detectable brittle earthquakes recently. The magnitude 4.8 on the southern margin in early May, the magnitude 5.7 and the magnitude 5.1 cluster on June 3rd, have tended to follow elevated tremor cycles. The pattern is not a deterministic predictor. Elevated tremor does not guarantee a brittle event will follow, but the pattern is consistent with the established geophysical mechanism by which slow, deep slip loads the shallow locked zone. Tremor goes up, stress on the upper interface goes up. The probability of brittle failure on the upper interface goes up. Sometimes the failure happens, sometimes it does not. Why does this matter for tonight? It matters because it provides, on the California side, a complete local mechanism that explains why the cluster is happening when it is happening. Elevated tremor counts on the deeper interface have been loading the locked southern segment for weeks. The locked segment has been 326 years past its last full margin rupture, longer than any inter-event interval documented in the past 4,000 years of paleoseismic record. The Gorda Plate has been internally deforming under the combined stress of Pacific Plate compression from the west and Cascadia subduction from the east, with the Gorda Ridge's spreading center contributing additional eastward push on top of all of it. Every piece of the California cluster has a local mechanism that explains it. The cluster is not, by itself, mysterious. It is the kind of thing the southern Cascadia margin produces when it is loaded, and the deeper interface has been pumping stress upward into the locked zone. The Kamchatka cluster also has a local mechanism that explains it. The 2024 magnitude 8.8 earthquake last July ruptured a substantial portion of the southern Kuril Kamchatka segment, but did not rupture the entire primed region. The unbroken neighbouring segment inherited a portion of the Coulomb stress that was redistributed when the 8.8 unloaded its own patch. That neighbouring segment is now hosting the present cluster. The Pacific Plate is converging on the Okhotsk microplate at 7 to 9 centimeters per year, the fastest subduction rate in the world. The Japan Meteorological Agency issued a Megaquake advisory on this region after the 2024 8.8, and the advisory has not been lifted. Every piece of the Kamchatka cluster also has a local mechanism that explains it. The cluster is not by itself mysterious either. It is the kind of thing the southern Kuril Kamchatka segment produces when it is loaded, and the previous large rupture has redistributed stress onto its neighbour. So we have two clusters, each of which has a complete local mechanical explanation for why it is happening, and each of which is sitting on a segment of subduction zone that is already under elevated institutional watch. That is the centred framing. Two independent loading clocks, two independent local mechanisms, two segments that the relevant national seismic authorities have been flagging for months as elevated hazard zones. The fact that both clocks have arrived at firing window states at approximately the same calendar moment is, on the centred reading, the most ordinary kind of coincidence. Two stopwatches that started ticking at different times happening to chime in the same hour because they were both close to their next chime. The thing is that reading is correct on the local level for each cluster considered separately, but it does not quite finish the question. The question that the audience-facing instinct keeps returning to is whether the two clocks were always going to chime in the same hour, or whether something about the calendar moment we're sitting inside has made both clocks tick a little faster at the same time. That question is the one the next several parts of this video investigate, and to start that investigation honestly, we have to talk about the largest object the audience has probably ever been asked to think about as a single object, the Pacific Plate itself, the 7,500 kilometers of ocean and lithosphere between the two clusters, and what it actually means for both ends of a single plate to be failing at once. Part 5. The largest plate on Earth is failing at both ends. Hold this number in your head for a moment. 103 million square kilometers. That is the area of the Pacific Plate. To put it in perspective, the total surface area of the planet Earth is approximately 510 million square kilometers. The Pacific Plate by itself accounts for roughly 20% of the surface area of the planet. It is larger than every other tectonic plate on Earth combined would need to merge into a single object to match. It is, by a substantial margin, the largest single piece of lithosphere on the surface of the Earth. That number is hard to feel. Most of us spend our lives moving across distances of a few hundred kilometers at most, between cities, between regions, between coastal areas. The Pacific Plate is approximately 11,000 kilometers across at its widest east-west extent, from the Mariana Trench off Guam to the East Pacific Rise off the coast of South America. It is approximately 10,000 kilometers from north to south, from the Aleutian Trench off Alaska to the Pacific-Antarctic Ridge in the Southern Ocean. The shortest distance from one corner of the plate to the opposite corner is, depending on which corners you pick, somewhere in the range of 7,000 to 9,000 kilometers, The two clusters we are tracking tonight, the southern Cascadia margin and the southern Kuril Kamchatka margin, sit at approximately diagonally opposite corners of this enormous plate. The straight line distance between them, measured across the surface of the Pacific Ocean, is approximately 7,500 kilometers. That distance is roughly the same as the distance from New York City to Tokyo. It is the distance a commercial airliner covers in about 10 hours of flight time. It is the distance across which, on any given day, weather systems and ocean currents and migratory birds and ships and satellites and submarine cables operate as routine matters of long-distance Pacific Rim activity. It is also the distance across which the question of whether stress at one corner of a plate has anything to do with stress at the opposite corner becomes a question the literature treats very carefully. Here is the basic mechanical situation. The Pacific Plate is, as we mentioned, a single rigid body. That word, rigid, is doing a lot of work in geophysics, and it does not mean the plate cannot bend or flex under stress. It does. The plate flexes by tens of meters across the regions where it is being subducted, as the leading edge curves downward into the mantle. It flexes upward where it rides over hot mantle plumes like the one beneath Hawaii. It contains internal faults along which it deforms slowly over millions of years. But on the timescale of months to years, and at the scale of the plate as a whole, it behaves as a single coherent object that transmits stress through itself the way a steel bar transmits stress when you push on one end and the other end resists. Push on one end of a steel bar. The push propagates through the bar as elastic stress, travelling at the speed of sound in steel, which is about 5 to 6 kilometers per second. By the time you have completed the push, the entire bar has redistributed its internal stress to accommodate the new boundary condition. The Pacific Plate works in a directly analogous way, except that the bar is 103 million square kilometers in area, and the speed of sound in oceanic lithosphere is about 6 to 8 kilometers per second. A stress change at one corner of the plate propagates across the plate in roughly 20 to 30 minutes. By the time half an hour has passed after a stress event on the eastern margin, the western margin has already received the elastic signal of that event. The communication is essentially instantaneous on the scale of weeks or months. What flows through that communication is small. This is the part the literature is careful about. The stress amplitudes that propagate from a large earthquake at one margin to the opposite margin are, at distances of 7 to 8,000 kilometers, on the order of 1 to 10 kilopascals. To put that in geological context, the tectonic stresses that drive earthquakes themselves are on the order of 1 to 10 megapascals, 3 to 4 orders of magnitude larger. A surface wave travelling across the Pacific from a Kuril Kamchatka magnitude 8 event arrives at the Cascadia margin carrying a stress amplitude that is at most 1/10,000th of the local tectonic stress at the receiving margin. The amplitude is small, it is however not zero, and the literature has been documenting cases for 30 years now where small stress amplitudes from distant large earthquakes do produce detectable triggered seismicity at the receiving margin, provided the receiving margin is already loaded near failure. We will get to that literature in detail in a few minutes. The point for now is just that the mechanical question, whether what is happening at one corner of the Pacific Plate has anything to do with what is happening at the opposite corner, is a real question with a real, partial, complicated answer. The answer is not no, the corners are independent. The answer is also not yes, they are coupled in any strong sense at the magnitudes presently observed. The answer is something more like, the corners are mechanically connected, the connection carries stress amplitudes that are tiny compared to local tectonic stress. The connection has been observed to produce triggered seismicity at hemispheric distances for source events above approximately magnitude 7.5, and the present clusters are an order of magnitude below that threshold. The connection is real, the amplitude is small, the threshold for detectable triggering is not met by the present events. That answer is not satisfying. It does not give you a clean yes or no. It gives you a careful, qualified statement of what the physics actually supports. The reason the answer is not cleaner is that the underlying physical system, the Pacific Plate, as a single rigid body with local stress accumulation at thousands of independent fault patches around its margins, is itself not a clean system. It is a heterogeneous, multi-scale, multi-mechanism system that produces detectable signal at some thresholds and not at others. The literature has done its best to characterize where those thresholds sit, but the thresholds are themselves not perfectly sharp, and the question of whether sub-threshold effects exist below the detection capability of the current global seismic network is a real open question that the formal research community continues to investigate. What this means for the present clusters is something like the following. If either of the present clusters were to escalate, if either side produced a magnitude 7 or larger event in the next several days, the question of whether the escalation triggered detectable secondary activity at the opposite margin would become a real and literature-supported question. The Hill, Velasco, Politz, and Brodsky papers we are about to walk through document exactly this kind of effect at exactly this kind of distance. At the present magnitudes, in the magnitude 5 range, the literature does not support a triggering claim. But the present magnitudes are not the only magnitudes the situation might evolve into. There is a second mechanical consideration worth naming explicitly. The Pacific Plate as a whole, over decadal time windows, can in principle accumulate transient stress asymmetries between its driving forces. If slab pull on the western margins runs slightly faster than ridge push on the East Pacific rise can compensate for, the plate as a whole spends a brief period under net tension. If the asymmetry reverses, the plate spends a brief period under net compression. These transient global stress states are difficult to measure directly with the present generation of geodetic instruments, but they have been inferred from satellite-based observations of plate kinematics over the last 20 years of high-precision GPS measurement at margin sites worldwide. The window of observation is still short relative to the timescales over which these asymmetries might oscillate. The honest scientific position is that smaller-scale plate-wide transient stress states probably exist below the present detection threshold, and that the question of how those transients interact with the loading clocks at individual margin segments is an active research area. If you are a scientist working on this problem, you are probably reading this part and saying that the description is oversimplified. It is. The actual mechanics of Pacific Plate stress redistribution at decadal timescales are much more complex than a single rigid bar push. They involve mantle flow at the base of the plate, viscoelastic coupling at the slab interfaces, segmentation of the subducting slabs into different mechanical zones, and a great deal of local geometry. The point of this part of the video is not to argue that the plate is a simple bar. The point is to establish that the plate is, mechanically, one object, and that the question of whether the present catalogue co-occurrence at its two opposite corners might reflect something beyond pure independent coincidence is a question with mechanical legitimacy at the level of basic physics, even if the literature does not currently support strong coupling claims at the magnitudes presently observed. That brings us to the question of what has been observed in the deeper historical record, because if you want to know how worried to be about the cluster developing off Kamchatka right now, the place to start is what the same trench has done before, in years when the cluster was the prelude to something much larger. The Kuril Kamchatka Trench has a long and well-documented record of producing some of the largest earthquakes in modern instrumental history, and the patterns of how those earthquakes loaded the segments around them are exactly the kind of context the present cluster cannot be understood without. Part 6. What 1952 looked like. In the pre-dawn hours of November 5, 1952, an earthquake of magnitude 9.0 struck the seafloor off the southern coast of the Kamchatka Peninsula. It became known, in the international seismological literature, as the Severokurilsk earthquake, named for the small Russian town on the northernmost of the Kuril Islands that took the brunt of the damage and the tsunami that followed. The event was the fifth largest earthquake ever recorded by modern seismographic instruments. It is exceeded in the instrumental record only by the 1960 Chile earthquake at magnitude 9.5, the 1964 Alaska earthquake at 9.2, the 2004 Sumatra-Andaman earthquake at magnitude 9.1 to 9.3, and the 2011 Tohoku earthquake at magnitude 9.1. Severokurilsk sits in that very short list of the largest events humans have ever measured. The rupture extended over approximately 600 kilometers of the southern Kuril Kamchatka Trench, from the southern tip of the Kamchatka Peninsula down through the northernmost Kuril Islands. The rupture was a megathrust event on the interface between the subducting Pacific Plate and the overriding Okhotsk microplate, in the same depth range and on the same kind of fault that produces the largest earthquakes Earth is known to be capable of generating. The fault patch that ruptured was loaded by tens of meters of accumulated elastic strain that had been building since the previous large event on that segment. When friction finally gave way, the seafloor lurched approximately 20 meters in a few minutes. That displacement of the seafloor is what generated the tsunami, The tsunami radiated outward from the rupture in all directions across the Pacific. It reached the southern Kuril Islands within 15 minutes. It reached the southern Kamchatka coast within 30 minutes. It crossed the open ocean and arrived in Hawaii roughly 6 hours after the earthquake, with wave heights at Hilo Bay of approximately 12 feet. It reached the western coast of South America in roughly 22 hours, with measurable wave heights at the Chilean coast. It was the most extensive trans-Pacific tsunami of the 20th century until the Sumatra-Andaman event of 2004. Approximately 2,336 people are believed to have died, most of them in Severokurilsk itself, where the town was inundated by waves up to 50 feet high within minutes of the earthquake. The exact death toll is disputed in the historical record because the Soviet government of the time did not publicly acknowledge the disaster for decades. The number 2,336 is the figure that has been derived from post-Soviet archive research, and is the figure that appears in the modern seismological literature. The real number may be higher. That was 1952. Now consider what came before it. The same general region, the southern Kuril Kamchatka system, had also produced a large event in 1923, the Kamchatka earthquake of approximately magnitude 8.5 on a more northerly portion of the same arc. The 1841 Kamchatka earthquake had been a comparably large event further to the north still. The 1737 Kamchatka earthquake had been another similar size event, recorded in Russian colonial archives from the early period of Russian exploration of the peninsula. The historical record of large Kuril Kamchatka events extends backward at least 3 centuries, with magnitude 8 and above events recurring on the various segments of the arc at intervals of 70 to 150 years for each individual segment. The pattern that the literature has converged on, after decades of analysis of this and other long subduction zone arcs, is that the segments do not rupture in isolation, but in clusters and sequences. A large event on one segment redistributes Coulomb stress onto the segments immediately adjacent to it. The redistribution can advance the failure clock on the adjacent segments by years to decades, depending on how loaded those adjacent segments already were before the redistribution. The pattern is sometimes called domino segmentation, although the analogy is imperfect because the segments do not fall in sequence over hours or days the way actual dominoes do. The pattern is more like a slow chain. One segment fires, stress shifts onto the next segment continues loading until it reaches its own failure state, fires, shifts stress onto the segment after that. The whole sequence can take decades to play out. The 1952 rupture redistributed stress onto the segments immediately to its north and to its south. The segment to the north hosted a magnitude 8.3 event in 1959, 7 years later, on the central Kamchatka portion of the arc. The segment to the south hosted progressively smaller events through the 1960s, a magnitude 7.5 event in 1963, a magnitude 7.5 event in 1969. The pattern of post-1952 activity is consistent with the standard domino segmentation model. Each event redistributed stress onto the adjacent segments. Each adjacent segment continued accumulating its own local strain on top of the inherited Coulomb stress increment, and each in its own time reached its own failure state. The same pattern repeated in different forms over the subsequent decades. The 1997 Kronotsky earthquake at magnitude 7.8, the 2006 Kuril earthquake at magnitude 8.3, the 2007 Kuril earthquake at magnitude 8.1, all sat on segments adjacent to or within the broader Kuril Kamchatka system, all happened in temporal proximity to previous large events on adjacent segments, all conformed to the basic shape of subduction zone segment by segment failure that the literature has come to expect. That brings us to what happened in July of last year, on the segment immediately adjacent to the segment hosting the present cluster, and to the institutional response that has been in place ever since. Because what happened in 2024 was not a routine event. What happened in 2024 was the most recent magnitude 8 and above earthquake on this arc, and it left an unfinished piece of fault that the global seismic community has been watching closely ever since, and that the present cluster sits squarely on. Part 7. The 2024 Earthquake That Didn't Finish. In late July of 2024, an earthquake of approximately magnitude 8.8 struck the southern portion of the Kuril Kamchatka Trench. It was the largest earthquake recorded anywhere in the world in 2024. By some independent measures, Depending on which moment tensor solution and which depth model is used, it was the largest earthquake recorded anywhere in the world since the 2011 Tohoku event in northern Japan. It ruptured a substantial portion of the southern Kuril Kamchatka segment, generated a trans-Pacific tsunami, and produced ground shaking that was felt across the entire Kamchatka Peninsula and into the northern Kuril Islands. The detail that matters for tonight is what the 2024 rupture did not do. The rupture did not extend the full length of the loaded segment. The relevant body of subduction zone segmentation research, including the literature on the 2011 Tohoku rupture's incomplete coverage of the northern Japan segment, has converged on the framework that megathrust ruptures on long subduction zone arcs frequently terminate short of the full geometrically capable length of the loaded segment. They terminate at structural barriers, places where the slab geometry changes, where the seismic coupling coefficient on the interface shifts, where the local hydrology of the interface changes. When the rupture terminates short, it leaves a piece of fault on the other side of the barrier that was not part of the rupture, but that was being loaded by the same long-term tectonic process. That leftover piece of fault, the unbroken neighbour segment, inherits a portion of the Coulomb stress that the ruptured segment redistributed when it failed. The unbroken neighbour is loaded by its own local tectonic process, plus the redistributed Coulomb stress from the ruptured neighbour. It is, in the language the field uses, advanced on its own failure clock. The 2024 magnitude 8.8 ruptured a southern portion of the Kuril Kamchatka segment, but terminated short of the full geometrically capable extent. The unbroken neighbour segment, the segment immediately to the north of the 2024 rupture's northern terminus, sitting between the 2024 rupture and the next major structural break further north on the Kamchatka portion of the arc, is the segment that the present cluster sits on. The present cluster is occurring within or immediately adjacent to the geographic zone of that unbroken neighbour segment. This is not a hypothesis. This is the conclusion that the Japan Meteorological Agency reached after analysing the aftermath of the 2024 event, and the basis on which the agency issued its Megaquake advisory on the southern Kuril Kamchatka and northern Japan Trench segment. The advisory was issued in the months following the 2024 event. The advisory has not been lifted as of the present recording. The advisory is, in effect, an official statement from the relevant National Seismic Authority that the segment is loaded, has been advanced on its failure clock by the redistribution of stress from the 2024 rupture, and warrants elevated public preparedness messaging. The advisory is not a forecast. The Japan Meteorological Agency, in its official documentation, is careful to specify that the advisory is not a prediction of any specific magnitude or any specific timeline. The advisory is a flag. It is a statement that the loading state of the segment is at a level where the conditional probability of a large event is elevated above the long-term background rate, and that residents of the region should prepare accordingly. The advisory has been the subject of considerable public attention in Japan over the past year, with detailed public communication about earthquake preparedness, tsunami evacuation routes, and household emergency planning. The agency has, in other words, treated this segment seriously. The institutional posture of the relevant National Seismic Authority toward the segment hosting the present cluster is one of elevated official watch. Now consider how the present cluster fits into that institutional posture. The cluster is producing 8 to 9 magnitude 4.5 and above earthquakes in 36 hours on the segment that is already under official elevated watch, with depth spanning the full interface and upper slab range in a tight spatial footprint with no Amori decay. The cluster is, in other words, doing exactly the kind of thing on exactly the segment that the agency has been watching for. Whether the cluster represents a precursor sequence that will lead to a larger event on this segment in the coming days or weeks, or whether it represents a routine elevated background that does not lead to a larger event, is the question that no national seismic authority anywhere in the world has the analytical tools to deterministically answer. The literature is consistent on this point. Earthquake prediction in the strong sense, being able to specify the magnitude, location, and timing of a future event within a useful window, is not currently within the technical capabilities of any agency anywhere in the world. The famous attempts at strong prediction, like the 1975 Haicheng evacuation in China that successfully evacuated a city before a magnitude 7.3 earthquake, have been balanced by the failures, like the 1976 Tangshan earthquake, which struck without warning the year after Haicheng and killed approximately 240,000 people. The Haicheng success was based on a complex pattern of foreshocks and other precursor signals that was, in retrospect, partly luck. The Tangshan event had its own pattern of precursors that the same prediction system failed to recognize at the time. The lesson the global seismological community took from the Haicheng and Tangshan experience, and that has been reinforced by decades of subsequent research, is that even in the cases where precursor signals exist, they are rarely distinguishable in real time from the background fluctuations of seismic activity. Strong prediction is, with present tools, not possible. What is possible is what the Japan Meteorological Agency is doing. The agency is monitoring the segment closely, maintaining the advisory, communicating public preparedness messaging, and watching for whether the present cluster escalates. If the cluster produces a magnitude 6 or larger event in the coming days, the institutional posture would tighten further. If the cluster produces a magnitude 7 event, the agency would activate the next tier of warning. If the cluster were to taper without producing a larger event over the next several days, the advisory would remain in place, but the immediate elevated concern would decline. These are the actual operational options the agency has. They are also the same options the United States Geological Survey has on the southern Cascadia margin tonight, where the California cluster sits on the segment that the United States National Seismic Hazard Map has long flagged as having approximately a 10% probability of producing a magnitude 9 and above full margin rupture in the next 50 years, with the Oregon Office of Emergency Management estimating a higher conditional probability around 37% for a magnitude 7.1 and above partial rupture in the same window. There is a piece of the 2024 event that deserves a closer look before we move on, because it determines how the present cluster should be interpreted in the context of what has already happened on this segment. The 2024 magnitude 8.8 is, by some measures, the second largest earthquake to strike anywhere on Earth in the last 15 years, behind only the 2011 Tohoku event. Its rupture extended over several hundred kilometers along the southern Kuril Kamchatka arc, displaced the seafloor by tens of meters in places along the rupture surface, generated a tsunami that propagated across the Pacific Basin and was recorded at tide gauges on the Hawaiian, Alaskan, and South American coasts. The event released approximately 10 to the 22nd joules of seismic energy, roughly 100 million times the energy of the magnitude 5.7 off Pistol River on June 3rd, roughly 10 million times the energy of the magnitude 5.2 off Kamchatka on the same date. The 2024 event was, in tectonic terms, a hugely energetic redistribution of stress within the southern Kuril-Kamchatka segment of the Pacific Plate. The portion of the segment that ruptured was, in the post-event analysis, characterized by several months of detailed source studies that mapped the slip distribution across the rupture surface. The slip distribution showed concentrated displacement in the central portion of the rupture, tapering to lower displacement at the northern and southern ends. The geometric edges of the rupture were not perfectly aligned with the geometric edges of the loaded segment. At the northern end of the rupture, the slip distribution tapered to essentially zero somewhere short of the structural barrier that the geometric and geodetic analysis had identified as the likely terminus of the loaded segment. That gap, the portion of the loaded segment that was not part of the 2024 rupture, is the unbroken neighbour segment that the present cluster is now sitting on. It is the piece of fault that the 2024 event left behind. It is, by the analysis the relevant agencies have made public over the past year, the most likely candidate for the next large event on this portion of the arc. The Coulomb stress redistribution from the 2024 rupture onto the unbroken neighbour has been quantified in several published papers in the months following the event. The estimates of the stress increment on the unbroken neighbour are in the range of 1 to 10 bars, depending on the exact geometry of the slip distribution and the depth at which the Coulomb stress is evaluated. To put that in scale, 1 bar is approximately 100 kilopascals, about 1/10,000th of the typical tectonic stress that drives subduction zone interface failure. A stress increment of 1 to 10 bars is small in absolute terms, but large in relative terms for the question of whether it advances the failure clock on the receiving segment. The literature on Coulomb stress triggering, including the foundational work of King, Stein, and Lin, published in the Bulletin of the Seismological Society of America in 1994, has documented numerous cases where stress increments of 1 to 10 bars on a loaded receiver segment have measurably advanced the timing of subsequent failures on that segment. The southern Kuril-Kamchatka unbroken neighbour, in other words, is in the stress state that the literature has documented as the kind of state where subsequent failure timing is meaningfully advanced. The Japan Meteorological Agency's Megaquake advisory on this segment is built directly on this analysis. The agency has access to the same published stress transfer studies that the international community has, plus the additional internal modelling that the agency does for its own operational forecasting. The advisory's existence is institutional acknowledgement that the agency considers the loading state of the unbroken neighbour segment to be at a level where elevated public preparedness is warranted. The advisory's failure to be lifted in the year since issuance reflects the agency's continued judgment that the loading state has not relaxed. 2 segments, 2 official elevated watch postures, 2 simultaneous clusters firing on those segments inside the same 48-hour window. From the perspective of the institutional response, this is not a normal week. From the perspective of the catalogue statistics, it is unusual but not unprecedented. From the perspective of the audience-facing instinct, the question is whether the simultaneity means more than the sum of the 2 independent events. And to answer that question rigorously, we have to go to the actual literature on what happens when one part of a tectonic system communicates with another part across long distances. Part 8. When surface waves cross the Pacific. In the summer of 1992, a magnitude 7.3 earthquake struck the Southern California desert at a place called Landers. It was the largest earthquake to strike the continental United States in 40 years. The event itself was a strike-slip rupture on a complex network of faults in the eastern Mojave Desert, with surface rupture extending for approximately 85 kilometers. By the standards of California seismicity, the Landers event was a major earthquake. By the standards of the global catalogue, it was a moderate event, large enough to produce significant ground motion in the source region, large enough to be felt across the western United States, but not large enough to belong to the catalogue of magnitude 8 and above ruptures that dominate the global earthquake energy budget. What made Landers important to the scientific question we're working on tonight is not the size of the event itself, but what happened in the hours and days following the rupture at locations far away from the source. Within minutes of the Landers main shock, seismographs across the western United States and into the Pacific Northwest began registering small earthquakes in places that had not been seismically active in the immediately preceding weeks. The Long Valley caldera in eastern California, 300 kilometers from Landers, produced a cluster of small earthquakes within hours. The Geysers geothermal field in northern California, 800 kilometers from Landers, produced an event within the first day. The Yellowstone caldera in Wyoming, more than 1,000 kilometers from Landers, produced an increase in microseismicity that was detectable on the regional networks. There were similar small clusters in several locations across the western United States, all within thousands of kilometers of the Landers source, all in the hours and days following the main shock, all in places that had been quiet immediately before. This pattern, the appearance of small clusters of earthquakes at distant locations following a large main shock, was the observational basis for what came to be called remote dynamic triggering. The literature on it begins in a substantial way with a paper by David Hill and colleagues published in Science in 1993. The paper documented the post-Landers clusters at multiple distant locations, demonstrated that the timing of the clusters coincided closely with the arrival of surface waves from the Landers main shock at each receiving location, and proposed the mechanism. Surface waves from a large earthquake carry transient stress amplitudes that propagate across the surface of the Earth at speeds of 3 to 4 kilometers per second. When those surface waves arrive at a distant location, they impose a transient stress on the local fault system. If the local fault system is already loaded close to its own failure state, the transient stress amplitude added by the surface waves can be enough to push it over the threshold and cause a triggered event. The triggered event releases the local accumulated strain, not the energy from the original distant source. The distant source provides the trigger, the local accumulated strain provides the energy. That paper opened a substantial body of subsequent research on remote dynamic triggering. The body of work has continued to grow over the subsequent 30 years, with successive papers documenting triggered seismicity at progressively longer distances from progressively larger source events. The 2004 Sumatra-Andaman earthquake at magnitude 9.1 to 9.3 produced documented triggered seismicity at locations across the entire planet. Events in California, in Alaska, in the Central Asian Plateau, in Mexico, in Southern Africa, in the high latitudes of both hemispheres. The paper that most thoroughly characterized the Sumatra-Andaman triggered seismicity worldwide was published by Aaron Velasco and colleagues in Nature Geoscience in 2008. The Velasco paper demonstrated that triggered seismicity from a magnitude 9 class source event was a genuinely global phenomenon, detectable at any location on the planet where local fault systems were loaded close to failure. The paper established that the triggering effect did not require the receiving location to be on the same plate as the source, did not require any particular tectonic relationship between source and receiver, and did not require the source event to be within any particular distance threshold. What it required was a sufficiently large source event and a sufficiently loaded receiving fault. A subsequent paper by Fred Politz and colleagues, published in Nature in 2012, examined a different magnitude class. The Politz paper analysed the 2012 East Indian Ocean earthquake at magnitude 8.6, which was a large but not 9 class event, and documented that even at the 8.6 level, the triggering effect was detectable globally at receiver locations that were loaded near failure. The Politz paper established that the magnitude threshold for global triggering effects was at least as low as magnitude 8.6 and quite possibly lower. Going down further in magnitude, a paper by Emily Brodsky and Stephanie Prejean, published in the Journal of Geophysical Research in 2005, examined whether triggered seismicity could be detected from source events below magnitude 8. The Brodsky and Prejean paper focused on a particular receiving location, the Long Valley caldera in California, and analysed the historical record of triggered events at Long Valley in response to a series of source events of various magnitudes at various distances. The paper concluded that the triggering threshold at this kind of well-loaded receiving location was somewhere in the magnitude 7.5 range. Events below magnitude 7.5 did not consistently produce detectable triggering at the most sensitive of receiving sites. Events above magnitude 7.5 did. The threshold is not perfectly sharp. Local conditions matter, the receiver geometry matters, the source mechanism matters, but the literature has converged on magnitude 7.5 as the rough lower bound for source events that produce detectable triggering at hemispheric distances. That is the relevant number for tonight. The literature supports remote dynamic triggering from sources at magnitude 7.5 and above. The literature does not support remote dynamic triggering from sources in the magnitude 5 to magnitude 6 range. The two clusters that are active tonight, on opposite sides of the Pacific Plate, are producing events in the magnitude 5.1 to magnitude 5.7 range. They are an order of magnitude below the threshold the literature treats as the lower bound for hemispheric triggering effects. What that means in practical terms is something the audience needs to hear clearly. The present clusters are not, by the existing literature, large enough to be triggering each other across the Pacific. The magnitude 5.7 off Pistol River, Oregon, on the morning of June 3rd, universal time was not large enough to send a surface wave across the Pacific that could have triggered the magnitude 5.2 off Kamchatka at 17:23 universal time on the same date. The surface wave amplitude at the Kamchatka receiver location from a magnitude 5.7 source 7,500 kilometers away is, by direct calculation, several orders of magnitude below the stress threshold at which any documented case of remote triggering has ever been observed. The hypothesis that the two clusters are causally coupled across the plate through dynamic triggering at the magnitudes presently observed is not supported by the literature. That is the honest debunking of one version of the strong coupling claim. The two clusters are not triggering each other through surface wave dynamic stress transfer. They cannot be at these magnitudes. The literature has, after 30 years of careful research, established the threshold below which the effect is not detectable, and the present clusters are below that threshold. Now, what would change that picture is straightforward. If either of the two clusters were to escalate into a magnitude 7 event in the coming days, the picture would change. A magnitude 7 event on either side would still be below the magnitude 7.5 threshold the literature treats as the lower bound for clear hemispheric triggering, but it would be much closer to that threshold than the magnitude 5 range events the clusters have produced so far. A magnitude 7.5 or above event on either side would clearly cross the threshold. If the southern Cascadia cluster were to escalate to a magnitude 7.1 partial rupture event, of the kind the Oregon Office of Emergency Management has flagged as having a 37% probability over the next 50 years, that event would generate surface waves arriving at the Kamchatka margin at amplitudes that the literature treats as triggering capable for a receiver in the loaded state the present cluster suggests. Similarly, If the Kamchatka cluster were to escalate to the kind of event the Japan Meteorological Agency advisory anticipates as possible, the surface waves arriving at the southern Cascadia margin would be triggering capable for a receiver in the loaded state that the past month of elevated tremor count suggests. The literature does not say the two corners are coupled at the present magnitudes. The literature does say that if either corner escalates, the coupling becomes a real and literature-supported question, and the opposite corner becomes a place where elevated, near-term, conditional probability of triggered activity would be expected to apply. The honest framing for the audience is something like this. Tonight, what is happening is not coupled across the Pacific in the strong sense that the conspiracy framing sometimes suggest. Tonight, what is happening is two independent local clusters on two independently primed segments that have arrived at firing window states at approximately the same calendar moment. If tomorrow, or the day after, either side escalates, that picture changes. Until then, the cleanest reading is independent loading clocks producing simultaneous catalog visibility. That cleanest reading is what we will develop more fully in the next part, but before we get there is one more piece of arithmetic that the audience deserves to see clearly. Because there is a version of the strong coupling claim that does not rely on the remote triggering literature at all, that instead invokes the solar storm passing through Earth's neighborhood at the same time as the two clusters, and that does not survive contact with basic energy budget calculation. That arithmetic, more than any other single thing, is what closes the door on the strongest forms of the conspiracy framings around weeks like this one. Part 9. The Energy Budget Problem. Earlier in this video we mentioned that the same 48-hour window that contains the two earthquake clusters also contains a major solar event. The active region on the visible solar disk numbered 4,455 produced an X 1.0 class solar flare at 11 hours and 19 minutes, universal time on June 3rd, preceded by an M9.3 flare and an M7.7 flare from the same region in the prior 10 hours. Multiple coronal mass ejections from the June 3rd sequence are in transit through the inner solar system. The NOAA Space Weather Prediction Center has issued a G3 strong geomagnetic storm watch valid for June 4th through 5th, and the official forecast discussion includes a textual note about the chance of isolated periods of G4 severe geomagnetic storming during the peak of the multi-CME passage. The solar wind speed at the Lagrange 1 position is currently in the 427 km per second range, and the BIS component of the interplanetary magnetic field has already excursioned southward to approximately -9 nanoteslas. The space weather event is genuinely happening at the same calendar moment as the two earthquake clusters. The independent observation cycle has noted this and speculated aloud about possible coupling. A version of the claim that circulates in the online conversation around weeks like this one is that the X-class flare, or the inbound coronal mass ejections, or the geomagnetic storm is somehow triggering the earthquake activity. The claim has several variants. Some versions invoke direct stress coupling between geomagnetic field changes and lithospheric stress states. Some versions invoke a more vague kind of energy transfer from the solar event to the Earth. Some versions invoke the high-frequency active auroral research program facility in Gakona, Alaska as a triggering mechanism. All of these versions, in their strong causal form, run into the same problem when you do the arithmetic. Let us do the arithmetic. An X 1.0 class solar flare releases approximately 10 to the 25th joules of total energy. That number is hard to feel, so let us put it in scale. The total annual energy consumption of the entire human civilization is approximately 10 to the 21st joules per year. An X 1.0 flare releases, in a few minutes, approximately 10,000 years of total human civilizational energy consumption. The number is staggering. The X 1.0 is the smallest of the X-class flares. Flares are classified on a logarithmic scale, so an X10 flare would release 10 times more total energy, an X100 1,000 times more. The X 1.0 that fired on June 3rd is a strong flare, but not an unusual one for an active sun. Now consider what fraction of that 10 to the 25th joules reaches the Earth in a form that could mechanically couple to the lithosphere. The flare itself radiates almost all of its energy as electromagnetic radiation across the X-ray and ultraviolet bands. That radiation reaches the Earth in about 8 minutes, the speed of light from the Sun. Almost all of it is absorbed in the upper atmosphere, primarily in the ionosphere and the thermosphere, where it ionizes atoms and heats the upper atmosphere by a few hundred to a few thousand Kelvin. The atmospheric coupling is significant. It is why radio communications can experience blackouts during X-class flares. but the mechanical coupling to the solid Earth below the atmosphere is essentially zero. The X-ray and ultraviolet radiation does not penetrate to the surface. It does not impose any measurable mechanical stress on rock at depths of even 1 kilometer below the surface, let alone the 10 to 45 kilometers where earthquake nucleation occurs. The coronal mass ejections are a different physical phenomenon. A coronal mass ejection is a large cloud of magnetized plasma, protons and electrons, ejected from the Sun's corona at speeds of several hundred to several thousand kilometers per second. The June 3rd sequence of coronal mass ejections, by the modelling that has been done at the NASA Space Weather Modelling Center, includes multiple ejections with total integrated kinetic energy of approximately 10 to the 24th to 10 to the 25th joules across the full sequence. That is, again, a very large number. But again, only a fraction of that energy reaches the Earth, and only an even smaller fraction couples mechanically to the solid Earth below the magnetosphere. The kinetic energy of the plasma cloud that intersects the Earth's magnetosphere over the few hours of a typical geomagnetic storm is roughly 10 to the 17th joules. Most of that is dissipated in the magnetosphere itself, in the ring current that builds up around the Earth during a geomagnetic storm, and in the ionospheric currents that flow at high latitudes during the auroral displays. The fraction that couples to the surface as induced current flow in the Earth's crust is a fraction of a fraction. Estimates from the literature on geomagnetically induced currents, the kind that affect power grids and pipelines, and long submarine cables during severe geomagnetic storms, put the total mechanical or electrical coupling to the crust at approximately 10 to the 10th to 10 to the 11th joules during a major storm. 10 to the 10th to 10 to the 11th joules of mechanical or electromagnetic energy reaches the solid Earth from a major geomagnetic storm. Now consider the energy of a magnitude 5.7 earthquake, the seismic moment release of a magnitude 5.7 event, calculated through the standard moment magnitude formula that relates seismic moment to the integrated displacement and area of the rupture surface, is approximately 6 times 10 to the 13th joules. The earthquake released 6 times 10 to the 13th joules of strain energy that had been stored in the rock at the source. Compare the two numbers. The coupled energy from a major geomagnetic storm to the solid Earth, at the upper bound of any estimate the literature treats as plausible, is approximately 10 to the 11th joules. The strain energy released by a single magnitude 5.7 earthquake is approximately 6 times 10 to the 13th joules. The ratio is approximately 1 to 600. The energy released by the earthquake is 600 times larger than the total energy delivered to the Earth's crust by the geomagnetic storm. And that is comparing a major geomagnetic storm to a single magnitude 5.7 earthquake. If you compared the storm energy to, say, the magnitude 8.8 Kamchatka event of 2024, the ratio would be more like 1 to 100 million. The implication is straightforward. The geomagnetic storm, at the largest size we have ever measured, does not deliver enough energy to the Earth's crust to trigger a magnitude 5.7 earthquake even once, let alone trigger a cluster of multiple magnitude 4.5 and above events on the two opposite corners of a plate the size of the Pacific. The energy budget does not support the claim. The honest framing is that the arithmetic forecloses the strong causal coupling between the solar event and the earthquake activity that is happening simultaneously with it. The same arithmetic, even more decisively, forecloses the claim about the high-frequency active auroral research program. The facility, at its maximum operating capacity, radiates approximately 3.6 megawatts of total electromagnetic power. To accumulate the energy released by a single magnitude 5.7 earthquake, the facility would have to operate at maximum power continuously for approximately 550,000 years. To accumulate the energy released by the 2024 magnitude 8.8, the facility would have to operate for approximately 1.5 billion years, roughly 1/3 of the age of the planet. The arithmetic is not subtle. The facility does not, cannot, and could never in any future configuration deliver the energy required to trigger the kind of seismic events the conspiracy framings attribute to it. There is also no known coupling mechanism between high-frequency radio transmission in the ionosphere and brittle failure of rock at the relevant depths. The literature does not contain a single paper proposing such a mechanism, and the basic physics does not provide one. These energy budget calculations are not a defense of the solar event being completely unrelated to anything happening on the planet. there is a measurable, weak, statistical correlation between solar activity and global seismicity over multi-decadal catalogues, documented in the work of Marchitelli and colleagues published in Scientific Reports in 2020. The correlation is real, and it is small, and the authors are explicit that the effect, if causal, operates as a small temporal modulator of earthquakes that were already loaded to failure, rather than as a generator of earthquakes that would not otherwise occur. The Marchitelli effect would not produce the dense, large amplitude clusters we are looking at tonight. It would, at most, slightly shift the day on which an already loaded earthquake fires. The strong claim that the X-class flare caused tonight's clusters is not what Marchitelli and colleagues claimed, and is not what the energy budget allows. That brings us back to where this video is going. The two clusters are real. They are happening on opposite sides of the Pacific Plate in the same 48-hour window. They are happening on segments that are already under official elevated watch. They are not, by the literature, triggering each other through remote dynamic stress transfer at the present magnitudes. They are not, by the literature, being triggered by the solar event. They are the kind of thing that happens on a global subduction zone catalogue when independent loading clocks at independent margin segments arrive at firing window states at approximately the same calendar moment, and the catalogue records both at the same time. The simultaneity is, in that framing, the kind of low probability coincidence the global catalogue produces a few times per year. But the framing has to leave room for what cannot yet be ruled out. The framing has to leave room for the possibility that each cluster, considered alone, is a more credible precursor than the routine baseline. The framing has to leave room for the possibility that smaller scale plate-wide transient stress states exist below present detection thresholds. The framing has to leave room for the possibility that what the catalogue is showing tonight is not the leading edge of anything bigger, and also has to leave room for the possibility that it is. Holding both of those possibilities open without collapsing into either of them is what the next part of this video tries to do. Part 10. What both clusters are actually doing. Here is where we stand. We have established that the cluster off Kamchatka is real, dense, sustained, and sitting on a segment that the Japan Meteorological Agency considers elevated. We have established that the cluster off the California-Oregon border is real, dense, sustained, and sitting on a segment that the United States Geological Survey considers elevated. We have established that the Pacific Plate is a single mechanical object that connects the two clusters at the level of basic physics. We have established that the literature on remote dynamic triggering does not support coupling between the two clusters at the magnitudes presently observed. We have established that the solar event happening at the same time is not, by energy budget arithmetic, capable of triggering the seismic activity. What we have not yet done is land on an honest, complete reading of what the two clusters together actually mean. We are going to do that now by walking through the three readings that the seismological community would consider defensible, ranking them by epistemic confidence, and naming explicitly which reading this video is centering. Reading 1 is the routine coincidence reading. Under Reading 1, the two clusters represent independent local activity on two independently loaded segments. Each segment has its own complete local mechanism that explains why it is firing when it is firing. The southern Cascadia margin is firing because 326 years of elastic strain accumulation on a segment with a paleoseismic recurrence range that maxes out around 291 years in the most recent 4,000-year window, combined with 2,694 catalogued tremor events in the past month on the deeper interface, have brought the locked patch close to failure on its own time. The southern Kuril Kamchatka margin is firing because the 2024 magnitude 8.8 rupture redistributed Coulomb stress onto its unbroken neighbour segment, and that neighbour segment has been loading on top of the inherited stress increment for the past year, and the natural settling has produced a cluster of moderate events as the segment continues to evolve toward whatever its eventual full failure state will be. Both mechanisms are local. Both mechanisms are complete on their own. The fact that they have arrived at firing window states at approximately the same calendar moment is, under Reading 1, a low probability coincidence. Not impossible. The global subduction zone catalogue produces this kind of coincidence at the low single-digit % per year rate, but not the modal pattern either. Reading 1 says the simultaneity is noteworthy in the same way that two unrelated friends happening to call you on the same evening is noteworthy. It is more striking than the average evening. It does not mean the two friends were coordinating. Reading 1 is the centered reading. It is the reading the literature most strongly supports. It is the reading we are landing on as the most defensible interpretation of what tonight's catalogue observation actually represents. It is also the reading that, taken alone, does not quite answer the question the audience-facing instinct keeps asking. The audience-facing instinct wants to know whether the two clusters tell us more together than they tell us apart. Reading 1 says they do not. Reading 1 says the two clusters tell us separately what each segment is doing locally, and the appropriate response is to take each segment seriously on its own terms. Reading 2 is the layered reading. Under Reading 2, the two clusters represent independent local activity on two independently loaded segments. That part is the same as Reading 1, but each cluster considered alone is a more credible precursor signal than the routine baseline catalogue activity would suggest. Under Reading 2, the southern Cascadia cluster, combined with the past month's tremor count pattern and the historical context of 326 years of quiescence past the maximum recent recurrence interval, represents an elevation in the conditional probability of a partial rupture event on the southern segment over a window of weeks. The literature on foreshock sequences, including the case studies of the 2011 Tohoku 51-hour foreshock and the 2014 Equeak 16-day foreshock sequence, supports the framing that a cluster of moderate events on a loaded segment elevates the conditional probability of a larger rupture on that segment, perhaps into the 5 to 15% range over a window of days to weeks, against a long-term background that is fractions of a percent. The same framing applies to the southern Kuril Kamchatka cluster considered alone, with the additional layer of the Japan Meteorological Agency advisory providing institutional confirmation that the segment is being officially watched. Under Reading 2, the appropriate response is to take each segment more seriously than Reading 1 suggests, while still treating the two clusters as independent expressions of independent local processes. Reading 2 is a watch and see reading. It does not predict. It elevates conditional probabilities on each segment considered separately. It is consistent with the institutional postures of both national seismic authorities involved, the United States Geological Survey on the Cascadia side, the Japan Meteorological Agency on the Kuril Kamchatka side. Both agencies are, in effect, operating in the Reading 2 posture tonight. They are monitoring more closely than baseline, communicating elevated preparedness messaging, and waiting to see whether either cluster escalates. Reading 2 does not endorse the plate-scale coupling framing that the audience-facing instinct sometimes reaches for, but it does endorse the framing that each segment alone is more interesting than the routine baseline would suggest. Reading 3 is the plate-scale transient reading. Under Reading 3, the Pacific Plate as a whole is currently in a transient stress state that is making both opposite margins more likely to fire in the same calendar window. The two clusters, under Reading 3, are not independently primed coincidences. They are jointly responding to a plate-wide condition that has elevated the failure probability on both margins simultaneously. The plate-scale transient could arise from various sources: an asymmetry between slab pull on the western margins and ridge push at the East Pacific rise, a slow, viscoelastic relaxation following the 2024 magnitude 8.8 that propagates through the plate at finite speed, an oscillation in the plate's overall kinematic state at decadal timescales that the present generation of geodetic instruments cannot resolve. Reading 3 is the reading that the audience-facing instinct in its strongest form articulates. It is the reading that says the two corners of the Pacific are talking to each other in a way that goes beyond independent loading clocks. Reading 3 is the most speculative of the three. The formal stress transfer literature does not support Reading 3 at the present magnitudes. The energy budget arithmetic, as we walked through in the previous part, does not support Reading 3 either at the magnitudes presently observed. Reading 3 is, in its strong causal form, not endorsed by the established literature on Pacific Plate mechanics. But Reading 3 is also not entirely fringe. The research community continues to investigate plate-scale transient stress states, and the question of whether such states exist below the detection threshold of present instruments is genuinely open. Reading 3, in its weak form, is something more like, there might be something we cannot yet measure that contributes to the simultaneity, and our inability to measure it does not prove it does not exist. That weak form of Reading 3 is a defensible scientific posture, even if the strong causal version is not. So where does this video land? The video lands on Reading 1 as the centered interpretation, with Reading 2 layered on top as the watch, and see addendum that applies to each cluster considered separately. The video acknowledges Reading 3 as the honest articulation of the audience-facing instinct, treats it with respect, and explicitly names that the strong causal version of reading 3 is not supported by present literature, while the weak version remains a defensible open scientific posture. That layered honesty is, in our view, the cleanest possible reading of what tonight's catalogue observation actually represents. The framing matters because the framing determines what the appropriate response is. Under reading 1 alone, the response is, "This is an unusual but not unprecedented catalogue coincidence. Monitor closely, no special action required." Under reading 1 with reading 2 layered on, the response is, "Each segment alone is more credible than baseline. Monitor each closely. Take the elevated conditional probabilities on each segment seriously, even though they remain at single-digit % levels." Under reading 3 in its weak form, the response is, "Watch for anything that would distinguish reading 3 from reading 1. Most notably, watch for escalation on either side, because any escalation would shift the weighted likelihood among the 3 readings substantially." That last point is where the video can give the audience something actionable to watch for in the coming days. The single observation that would most decisively shift the reading is a magnitude 7 event on either side. If the southern Cascadia cluster were to produce a magnitude 7 or larger event, the foreshock interpretation of the past 48 hours of California cluster activity would be confirmed for that segment. The conditional probability of a larger Cascadia event would elevate substantially, and the remote dynamic triggering literature would suggest the Kuril Kamchatka side becomes a real and literature-supported question. The same applies in reverse for an escalation on the Kuril Kamchatka side. The absence of such an escalation in the coming days does not confirm safety. It does not disprove the foreshock interpretation, only weakens it. But it does shift the centered reading further toward reading 1 alone. The watch window is, by the literature's own framing, days to weeks. Over the next several days, what happens on these 2 segments will tell us substantially more than what we know tonight. Part 11. Omori, Both, and why neither cluster is tapering. The framing we just developed depends on a set of basic statistical patterns that the global seismological community uses to characterize aftershock sequences. 2 of those patterns are worth understanding directly, because they are the patterns the present clusters either do or do not conform to, and the answer to whether they conform changes how we interpret what is happening. The first pattern is Omori's law. Omori's law was originally formulated by Fusakichi Omori in 1894, based on his analysis of the aftershock sequences following major Japanese earthquakes in the late 19th century. The modern form of the law, refined by Tokuji Utsu in 1961 and used in essentially all subsequent aftershock analysis, states that the rate of aftershocks following a main shock decays roughly as the inverse of the time since the main shock. If a magnitude 6 event is followed by 10 aftershocks in the first hour, the law predicts approximately 5 aftershocks in the second hour, 3 in the third, 2 in the fourth, 1 in the eighth, and so on, with the rate dropping smoothly along an inverse time curve. The law is not perfectly precise. There is local variation in the exponent of the decay, and the precise constants vary by tectonic setting. But the basic shape of the curve is highly consistent across thousands of documented aftershock sequences worldwide. Aftershocks decay, they decay on a predictable inverse time curve. That is what aftershocks do. The 2 clusters tonight are not behaving like aftershock sequences under Omori's law. The southern Cascadia cluster's largest event was the magnitude 5.7 at approximately 10 hours and 53 minutes universal time on June 3rd. Under Omori decay, the cluster should be producing approximately 1/10 as many magnitude 4 and above events at 12 hours after the main shock as it produced in the first hour, approximately 1/20 at 24 hours, approximately 1/40 at 48 hours. Instead, the cluster has continued producing magnitude 4 and above events through the evening of June 3rd Pacific time and into the morning of June 4th, well into the time window when Omori decay would have the rate tapering towards 0. The cluster is not tapering, it is sustaining. The same applies to the Kuril Kamchatka cluster. The largest event so far is the magnitude 5.2 at 17 hours and 23 minutes, universal time on June 3rd. Under Omori decay, the cluster should be tapering by now, 24 hours and more after the largest event. Instead, the GFZ German Research Center for Geosciences reported a magnitude 5.1 at 1713 universal time on June 4th, almost exactly 24 hours after the largest event. A magnitude 5.1 is, in magnitude terms, only slightly smaller than the magnitude 5.2 that came 24 hours earlier. The cluster is not tapering, It is sustaining a comparable event rate. What does it mean when a cluster does not show a Mori decay? It means the cluster is not, structurally, a single main shock plus aftershock sequence. It is something else. The two most plausible somethings are these. Either the cluster is a series of multiple discrete fault patches firing on a regional stress increment, in which case each patch has its own local main shock plus aftershock sequence that overlaps the others in time and gives the appearance of a sustained rate. Or the cluster is responding to a sustained ongoing stress source, in which case the events are not aftershocks of any one earlier event, but independent ruptures driven by a continuing increment in the local stress state. Both of those somethings are consistent with the framings developed in the previous part. Both are also consistent with the foreshock interpretation that reading 2 layered onto reading 1 allows for. The second pattern is Both's law. Both's law, formulated by Marcus Both in 1965, states that the largest aftershock of a main shock is typically about 1.2 units of magnitude smaller than the main shock. A magnitude 6 main shock would typically produce a largest aftershock around magnitude 4.8. A magnitude 7 main shock would produce a largest aftershock around magnitude 5.8. The law is not deterministic. Individual cases can vary by half a unit or more in either direction, but the average across hundreds of documented sequences is highly consistent at the 1.2 unit gap. Applied to the present clusters, Both's law predicts the following. If the magnitude 5.7 off Pistol River were the main shock of an ordinary aftershock sequence, the largest aftershock should typically be around magnitude 4.5. The cluster has in fact produced multiple magnitude 4.5 and above events following the magnitude 5.7, which is at or slightly above the Both prediction. If the magnitude 5.2 off Kamchatka were the main shock of an ordinary aftershock sequence, the largest aftershock should be around magnitude 4.0. The cluster has produced multiple magnitude 4.5 and above events, including the magnitude 5.1 24 hours later, well above the Both prediction. The Kuril Kamchatka cluster is, in particular, not behaving like a single main shock sequence under Both's law. The continued production of magnitude 5 class events suggests the cluster has not yet reached its largest event, or that the cluster does not have a single main shock structure to begin with. A third statistical framework worth naming is the Gutenberg-Richter magnitude-frequency relation. The relation, formulated by Benno Gutenberg and Charles Richter in the 1940s, states that for every one earthquake of a given magnitude on a given fault system, there are approximately 10 earthquakes of 1 magnitude unit smaller. A region that produces 1 magnitude 7 event will produce approximately 10 magnitude 6 events and 100 magnitude 5 events in the same time window. The slope of this relation, what the field calls the B-value, varies slightly across tectonic settings, with most subduction zone interfaces showing B-values close to 1.0, meaning the 10-to-1 ratio holds approximately. Applied to the present clusters, Gutenberg-Richter gives a conditional baseline. A cluster that has produced several magnitude 5 and above events would, under the standard B-value of 1.0, be expected to also produce roughly 1 magnitude 6 event for every 10 magnitude 5 events. The clusters have produced perhaps 10 magnitude 5 and above events between them so far. Under the simple statistical extrapolation, the conditional probability of a magnitude 6 event in the next several days from either cluster is in the low single-digit % range. The conditional probability of a magnitude 7 event is in the fractions of a % range. These probabilities are, again, conditional baselines. They are what you would expect from extrapolating the present cluster activity under standard statistical assumptions. They are not predictions, but they do provide a calibration point for how the conditional probabilities compare to the long-term background rate of magnitude 7 and above events on these segments, which is much lower. There is one more piece of statistical infrastructure worth naming, because it determines how to weight the absence of larger events so far. The conditional probability that a cluster like the one off Kamchatka, having already produced 1 magnitude 5.2 and 1 magnitude 5.1, eventually produces a magnitude 6 event. Somewhere in its evolution is, by the standard B-value extrapolation, in the range of 15 to 25% over the lifetime of the cluster. The corresponding conditional probability of eventually producing a magnitude 7 is closer to 2 to 4%. These conditional probabilities do not deterministically predict anything about what will happen on any given day. They are the calibrated baseline that the global subduction zone literature has converged on for what clusters of this size and density tend to produce, when the entire cluster lifetime is considered. The southern Cascadia cluster has a slightly different calibration because the Gorda plate has a higher B value than typical megathrust interfaces, meaning its clusters tend to produce a higher ratio of small to large events. But the basic shape of the calibration is similar. The combination of these three patterns gives us, for each cluster, a picture that looks like the following. The cluster is sustaining its event rate beyond what a Mori decay would predict for a routine aftershock sequence, which is consistent with multiple patch failures on a regional stress increment. The largest events so far are consistent with Borth's law for one possible main shock magnitude in the cluster, but are also consistent with the cluster not having yet reached its largest event. The Gutenberg-Richter conditional baseline gives a low single-digit % probability of a magnitude 6 in the next several days from each cluster, with magnitude 7 conditional probability in fractions of a percent. None of these patterns proves anything about what will happen next. All of them, together, characterize each cluster as more interesting than routine catalogue background, and as deserving the watch and see posture that reading 2 layered on top of reading 1 supports. The final piece of the picture is the question of whether the 2 clusters' simultaneous deviation from Omori decay and Borth's law has any joint significance beyond the sum of their independent deviations. The honest answer is that the simultaneity adds modest weight to the framing that something more than pure coincidence is happening, while not crossing the threshold at which the literature would treat the joint deviation as evidence of plate-scale coupling. The reading 3 weak form, the position that something might be contributing to the simultaneity that we cannot yet measure, remains a defensible scientific posture. The reading 3 strong form remains unsupported by present literature. We are now in a position to bring all of this together and ask what the catalogue co-occurrence we are looking at tonight actually represents from a broader statistical perspective. That perspective is what the next part of the video develops. Part 12. The pattern. The catalogue sees. Step back from the individual clusters for a moment and look at what the global earthquake catalogue is showing across the past 48 hours. Worldwide, the average rate of magnitude 4.5 and above earthquakes is approximately 50 per day, or roughly 2 per hour spread across the entire planet. Most of those events occur on subduction zone margins or transform fault systems, the active tectonic boundaries that produce essentially all of the world's seismic energy. The Pacific Ring of Fire, the loop of subduction zones and transforms that runs around the margins of the Pacific Plate, hosts approximately 40% of all magnitude 4.5 and above earthquakes worldwide. The Pacific Plate is, in catalogue terms, where most of the action happens. Inside the Ring of Fire, the activity is not uniformly distributed. It is concentrated in clusters on individual segments of subduction zones, on individual transform faults, on individual structural complexities at plate boundary intersections. On any given day, you can scan the global catalogue and find 1 or 2 locations where the local activity rate is elevated above the long-term background. A cluster on the Java Trench, a cluster on the Tonga Trench, a cluster on the Aleutian Trench, a sequence following a moderate event in Chile. Localized cluster activity is the normal state of the global subduction zone catalogue. What is less normal is the simultaneous appearance of 2 such clusters on opposite corners of the same plate. The statistical estimate for the probability of 2 such clusters firing simultaneously on opposite corners of the Pacific Plate within a 48-hour window can be derived in a few different ways. The simplest approach is to count in the historical catalogue how often 2 clusters of comparable magnitude and density have appeared on opposite Pacific corners within a comparable time window. The answer, from various analyses of catalogues going back to the 1960s, is on the order of 1 to 3 times per year. That is, the kind of simultaneous catalogue co-occurrence we are seeing tonight happens at a rate of approximately 1 to 3 times per year on the global Pacific Rim catalogue. It is not vanishingly rare. It is not the most common pattern either. It sits in the range of unusual but not unprecedented, occurring at the low single-digit % rate per day. That statistical anchor matters because it determines how we should weight the simultaneity itself. If the simultaneity occurred at a rate of once per decade, we would weight it much more strongly as evidence of something beyond pure coincidence. If it occurred at a rate of once per day, we would weight it as routine catalogue noise. At 1 to 3 times per year, the simultaneity falls in the range where the appropriate response is noticeable, worth investigating, not strong evidence of anything by itself. That is, in essence, exactly the response this video has been building toward. There is, however, a second statistical anchor that adds weight to the present case. The two segments where the present clusters are firing are not just two random subduction zone segments on the Pacific Rim. They are two segments that the relevant national seismic authorities have flagged as elevated hazard zones. The southern Cascadia margin is the subject of long-standing United States Geological Survey hazard modelling that places the conditional probability of a magnitude 9 and above full margin rupture in the next 50 years at approximately 10%, and the Oregon Office of Emergency Management figure for a magnitude 7.1 and above partial rupture at approximately 37% in the same window. The southern Kuril Kamchatka margin is the subject of an active Japan Meteorological Agency Megaquake advisory issued after the 2024 magnitude 8.8 and not lifted as of this recording. Both segments are not just on the Pacific Rim, they are on the parts of the Pacific Rim that the global seismological community has already flagged for elevated attention. The probability that two simultaneously firing clusters happen to land on two simultaneously flagged segments, conditional on the simultaneity itself happening, is harder to estimate but is plausibly in the low tens of percent. There are perhaps 8 to 12 segments worldwide that are currently under formal elevated official watch. The United States Geological Survey's hazard map highest categories, the Japan Meteorological Agency's Megaquake advisory zones, the Chilean Servicio Sismológico Nacional's monitoring of the Iquique Gap, the Peruvian Instituto Geofísico's monitoring of the southern Peruvian segment, and a handful of others. If the simultaneous catalogue co-occurrence we see tonight had landed on two random ring of fire segments, that would be a less interesting alignment. The fact that it landed on two of the 8 to 12 formally flagged segments shifts the conditional probability that the alignment is non-random somewhat upward. Not dramatically upward. The alignment is still consistent with random chance, but not negligibly upward either. These statistical anchors do not resolve the question of whether the simultaneity means more than independent coincidence. They give us a calibrated sense of how unusual the catalogue observation actually is, 1 to 3 times per year for the simultaneity itself. The institutional alignment shifting the weighting modestly toward this particular instance is more interesting than the average case of the simultaneity pattern. The cluster activity within each cluster sustaining beyond a Mori decay, suggesting that each cluster individually is more credible as a precursor signal than routine background. The literature unable to determine whether the joint pattern is leading or coincident over the relevant days to weeks window. A version of this assessment that the audience may find useful to carry forward is this. The present catalogue observation is in the range of unusual catalogue co-occurrences that happen on the Pacific Rim a few times per year. It is on segments that are already officially elevated. Each segment alone is showing within cluster patterns that are more credible than routine. The literature cannot yet determine whether the joint pattern means anything beyond the sum of its parts. The Honest Watch window is days to weeks. The cleanest monitoring posture is to track both segments, to refresh the catalogue daily, and to not overweight the absence of escalation as confirmation of safety, nor the presence of continued moderate events as confirmation of imminence. The literature has been more wrong than right when it has tried to make stronger predictions than that on actively developing earthquake clusters, and the discipline that decades of attempted prediction have taught the global seismological community is to hold the question open rather than collapse it prematurely into a conclusion the data does not yet support. That brings us to the closing question of the video, the question we have been working toward across all 12 parts, the question that the title of this video gestures at, and that the central narrative thread has been organised around, and that the audience-facing instinct keeps returning to no matter how rigorously the literature is parsed. Part 13. What Tonight Means. There is a simple version of what tonight means that fits in one sentence. 2 earthquake clusters fired on opposite corners of the Pacific Plate within 48 hours, both still developing as this video is being recorded, both on segments already flagged at the institutional level as elevated hazard zones, and the cleanest reading of the catalogue is independent loading clocks, producing coincident catalogue visibility on a pattern that occurs on the global ring of fire a few times per year. That is the centered reading. It is the reading the literature supports. It is the reading this video lands on as the most defensible interpretation. There is also a longer version of what tonight means that requires sitting with for a moment before settling into the simple version, because the longer version is what the audience-facing instinct keeps reaching for, and the longer version deserves a respectful articulation rather than a dismissive collapse into the centered reading. The longer version is this. The Pacific Plate is one object. It is the largest single mechanical object on the surface of this planet. It moves as one body. Its internal stress state is, in principle, integrable across its full extent. The two opposite corners of the plate are connected by the rigid body between them, and elastic stress propagates across that body at the speed of sound in rock, which is a speed fast enough that the connection is, on the scale of months, essentially instantaneous. The literature on remote dynamic triggering has documented that surface waves from magnitude 7.5 and above events travel across hemispheric distances and impose detectable triggering effects on receiver locations that are loaded near failure. The literature on plate-scale stress transients has been able to detect smaller stress oscillations at the level of the present generation of geodetic instruments, with the honest admission that smaller oscillations below the present detection threshold probably exist but cannot yet be measured directly. The basic mechanical and statistical infrastructure for thinking about whether the two opposite corners of the Pacific Plate could be communicating in a way that is not yet measurable, but that nonetheless contributes to the simultaneity of catalogue visibility on a pattern like the one tonight, is, in the literature's own framing, an open scientific question that the discipline continues to investigate. What that means in plain language is something like the following. At the present magnitudes, the magnitudes the two clusters have produced so far, the literature does not support a strong causal coupling between them. Each cluster has its own complete local mechanism. The simultaneity is, at the present magnitudes, a coincidence that occurs on the global catalogue a few times per year. Holding that as the centred reading is the right thing to do, but the literature also leaves room for what cannot yet be ruled out. The literature leaves room for the possibility that smaller-scale plate-wide transient stress states exist below the present detection threshold, and contribute modestly to the simultaneity of catalogue visibility on weeks like this one. The literature leaves room for the possibility that what we see tonight is the first weak signal of something the global instrument network does not yet have the resolution to characterize. The literature is honest enough to admit that the question of what the catalogue records cannot yet answer with full confidence. The catalogue tonight is recording two simultaneous clusters on two opposite Pacific corners on two officially flagged segments. The catalogue cannot tell us whether the two clocks happen to align by chance, or whether something larger that we have not yet learned to measure is contributing to the alignment. There is a question every seismologist watching this pattern is asking tonight, whether they say it out loud or not. The question is not whether the simultaneity is suspicious, or whether the conspiracy framings have merit. Those questions have been answered by the energy budget arithmetic and the literature on remote dynamic triggering, and the answers are firmly no. The question is whether the cluster on the southern Cascadia margin, alone and on its own terms, is the leading edge of the partial rupture that the recurrent statistics have been suggesting for several years now. The question is whether the cluster on the southern Kuril Kamchatka margin, alone and on its own terms, is the precursor to the next large event on the segment that the Japan Meteorological Agency has been watching since the 2024 magnitude 8.8. The question is whether each segment alone, considered separately under reading 2, is showing the kind of precursor pattern that the literature has documented in cases like the 2014 Iquique 16-day foreshock sequence and the 2011 Tohoku 51-hour foreshock. Those questions are real. Those questions are honest. Those questions are what the discipline does not yet have the tools to deterministically answer, even now, decades into the era of high-resolution seismic monitoring. The window over which those questions answer themselves is days to weeks. If either cluster escalates in the coming days into a magnitude 6 or larger event, the framing changes. If a magnitude 7 event happens on either side, the framing changes much more. The foreshock interpretation for that segment is essentially confirmed. The conditional probability of a still larger rupture on that segment elevates substantially, and the question of remote dynamic triggering of the opposite margin becomes a live literature-supported concern. If neither cluster escalates in the coming days, and both gradually taper into background, the centered reading of independent loading clocks producing coincident catalogue visibility becomes the conclusion of the entire episode, and the simultaneity becomes a noted but unremarkable case in the global record of such patterns. There is no way to know which of those outcomes the next several days will produce. The literature openly admits that. Every national seismic authority watching these segments openly admits that. The honest scientific posture is to hold the question open, monitor closely, and treat the centered reading as the most defensible interpretation, while remaining alert to the possibility that the layered reading 2, or the weak form of reading 3, may yet turn out to be the right framing. The catalogue does not, by itself, allow stronger statements than that. The literature does not allow stronger statements than that. The discipline has been more wrong than right whenever it has tried to make stronger statements than that on actively developing patterns like the one tonight. What we can do, in the meantime, is name what we are looking at clearly. 2 clusters, 2 corners of the same plate, both still developing, both on segments already flagged at the institutional level, both inside the same 48-hour window. The pattern is real. The catalogue has recorded it. The discipline will study it for years after these days have passed, regardless of how the next few weeks unfold. The catalogue is, tonight, a kind of mirror. The 2 halves of the mirror are firing at the same time. The mirror is showing us something about the state of the largest mechanical object on the surface of the planet. What that something is, in the deeper sense, is the question that no instrument on Earth can presently answer. There is a kind of stillness that settles in when you watch a pattern like this one. Not panic, not certainty, something else. Something more like the way a doctor watches a slow developing condition that may or may not become serious, monitoring the signs, refreshing the imaging, holding the diagnostic question open because the body has not yet declared what it is going to do. The Pacific Plate tonight has not declared what it is going to do. The 2 corners are showing us that they are loaded. The catalogue is showing us that the loading is visible. The literature is showing us that the visibility is unusual but not unprecedented. The discipline is showing us that the question of what the pattern means in the deeper sense remains, for now, open. We will know more in the coming days. The catalogue will continue to record. The institutional postures of the relevant national seismic authorities will tighten or loosen depending on what happens next. The question of whether tonight was a notable but ultimately routine catalogue coincidence, or whether it was the early visible signature of something larger that the global record has not yet seen, will resolve itself over a window of days to weeks rather than years to decades. The watch is what we do until it resolves. For now, what we have is this. 2 clusters, 2 corners of the same plate, both still developing. The mirror is showing us something, and the only honest thing left to say tonight is that, whatever it is showing us, the next several days are when the picture will start to come into focus.